Hello everyone. Welcome to our final project presentation. Today I'm going to introduce our work on visual object tracking. First, what is a visual object tracking? It's a key task in computer vision where we aim to continuously locate the object across the video frames. However, real-world challenge like occlusion, scale change, background clutters, and multiple moving target make this task very difficult. Video tracking is widely used in areas such as autonomous driving, security, surveillance. In our project, we implement and compare three representative tracking methods. The first is the Siamese FC, only can track the single object, and the deep sort, and the third is the ByteTrack. I will introduce these three methods separately. First, let's look at the Siam FC. This model uses a Siamese neural network to compare the target template and the search region. Both input go through the same convolutional network, and the feature are compared to find the most similar region. As you can see from the diagram, the network generates the embedding for both input, calculate the distance, and give a response map at the indicate the object location. Siamese FC is fast and simple, make it good for real-time applications. However, it only supports a single object tracking, and its performance drops in the crowd scenes. Two input pass through the indicate CNN to generate the feature embedding. The distance between the embedding is used to estimate whenever they represent the same object. Next, we use a deep sort. It is not a single model, but a complete tracking system. As shown in this figure, we use a ULV-8 to detect the object. Then we use a Kalman filter to show the path. Deep sort also uses a deep appearance feature extractor to help match object between frames. This helps maintain constant ID across the frame, even when people move fast or across with each other. However, deep sort depend heavily on the detection quality. The error in detection can break the tracking. Here you can see the example, the deep sort in action. First, each person is detected and labeled using the ULV-8. Then deep sort assign the ID to each person and keep the same ID across the frame. So you can see the same people like ID 12, they move down a little bit, and the system track them across different frame using both motion traction and the appearance feature. The third one, we implemented the ByteTrack, a newer multiple object tracker that does not rely on the appearance feature. ByteTrack uses two-stage association strategy. First is match detection with high confidence scored. Then it takes a low confidence detections, which would normally be discarded, then try to match them to the remaining tracks. This allowed the ByteTrack to recover from the occlusion and handle a crowd sense better. As shown in the diagram, the key innovation is the second match phase use a low confidence box. ByteTrack is also faster and simpler than deep sort and still achieve the very high accuracy.
Here I will talk about the theory and dataset of our project. Object tracking is the task of following the same object as it moves across different video frames. It is commonly used in applications like autonomous driving. In this project, we focused on two main types of tracking: single object tracking, or SOT, and multiple object tracking, MOT. In single object tracking, we only track one target throughout the video. We used a model called SIMFC. It works by comparing how the object looked in the first frame with how it looks later in the later frames. Using a simple three-layer convolutional neural network, it's fast and lightweight, but not suitable when you need to track multiple objects. Multiple object tracking means tracking several objects at the same time. In this project, we built two pipelines using the YOLO V8 detection model. One pipeline combines YOLO with deep sort, and the other with ByteTrack. These help keep track of each object's identity as they move through the scene. YOLO stands for You Only Look Once. It is a real-time object detector. For each frame in a video, YOLO draws bounding boxes around the detected objects and it gives a confidence score. This detection step is used at the beginning of both MOT pipelines. In the first pipeline, we use deep sort to track each object from frame to frame. Deep sort uses a Kalman filter to predict where an object will be next, and an appearance model to tell similar-looking objects apart. It works well when scenes are not too crowded. The second pipeline uses ByteTrack instead of deep sort. ByteTrack improves tracking by using not just confident detections, but also low confidence ones. This helps recover tracks that may have been missed, especially in crowded scenes where objects get blocked or partially detected. To test our tracking models, we used two public datasets. MOT20 is used for multi-object tracking in crowded scenes, while OTB100 is the benchmark for single-object tracking across different real-life challenges. Here I'll talk about the MOT20 first. MOT20 contains 4 high-resolution videos, each with between 600 and 1600 frames. Every frame includes detailed bounding boxes and object IDs. It captured at 25 frames per second and shows real-world scenes with the dense pedestrian traffic. MOT20 is very challenging. People often overlap and block each other, which makes it hard to track them correctly. Complex movement increases the chance of losing track or switching identities. The dataset also requires strong computing power due to its size and resolution. OTB100 contains 100 videos, and each one focuses on tracking just one object. Each frame is labeled with a bounding box. These videos include real-world issues like objects being blocked, moving quickly, changing shape or size, and changing light. OTB100 is used to test how precisely a model can stay focused on one object, even when the object is partly blocked, moves fast, or changes appearance. The model needs to keep tracking it accurately. Unlike the MOT20, it's about following just one target with precision.
Next, I'm going to introduce the section 3, which is the object tracking in the YOLO-based framework. It's a ByteTrack and also the deep sort integration for our project. So for the tracking integration in the YOLO framework, so this section we want to focus on the integration like of the tracking algorithm within the YOLO framework, and also the YOLO object detection alone is cannot maintain the temporal identity across the video frames. Also, we incorporate with the two multi-object tracking algorithm, which is deep sort and also the ByteTrack. And the purpose is for extend the YOLO's detection in the consistent object tracking. And also this goal is to ensure the robust ID assignment, also reduce the identity switches, and also like achieve the accurate tracking within in the quad or awkward environment. And also, as you can see these figures, this is our the visualizations system flowchart of our presentation of our project. So first we have the video input, and then we do the frame extraction, and also then we use the YOLO V8 model to do the object detection, and then we get like some parameters, like for example the X, Y, WH parameters, and also the detection box. So then we just feed those data and parameters to the tracking model, which is backtrack or the deep sort. Then it can be like do the tracking with the IDs. So the YOLO alone is not enough for the project tracking. So why the tracking is needed? So because the YOLO detection are just good at detecting the object frame by frame, and also its lack of the ability to link those detection over time. And also this become a limitation when trying to track the object across some consistent frame. For example, assigning consistent IDs for maintaining the trajectories, and also to address this. So we just decide to integrate the multi-object tracking algorithm, backtrack, or the deep sort. So as you can see from this figure, so it can be directly shows like you can see from this person and from here. So the backtrack is the algorithm is a little bit faster in the tracking the object, and also among this, like the backtrack is perpendicular is pretty it's a little bit efficient, and also the performance alternatives like the deep sort in the speed, and also in the enabling the real-time robust tracking. So next is the first step. We just like to the frame extraction used, and also the each video is composed decomposed into the individual image frames, and also the frames are treated as static images for the object detection. And also we enable the consistent per frame object localization. So the tool we use is the OpenCV for the video to frame extraction, and also the frame format is the sequential PNGs or the JPGs. So the second step is YOLO V8 detection pipeline. So in this section, we just using the YOLO V8N module, and also the YOLO V8N S module. So the purpose that because we want to locate it and also classify the object which such as vehicles or people, the person in each frame. So this is an example like how the output should be look like. So first for the output, we have the first label the cars or bus example in here. And also second, we have the confidence source, such as we have 70 in the left-hand side, and also we have 65 in the right-hand side. And then so also we can get the bounding box coordinates such as X, Y, WH. So the X, Y is just represent the top left corner, and also the W and H is the width and also the height of the image. So we use the YOLO to determine the location of the regulant object, and also its head, and also its coordinates inside those image. And so why this format is matters? So because the tracking algorithms such as the backtrack or the deep sort, they are all requiring the object coordinates to like predict motion, and also confidence source for the building, and also the X, Y, WH. This format is especially used for the Kalman filter and also the IOU calculation. So for the third step, so we have tracking mode. So we just basically in this project, we just we just use the YOLO V8 and also the backtrack or the YOLO VH with the deep sort. So once the boundary box is the coordinates and also the object size are obtained from the YOLO V8. So this is structure structure detection output is passed into the tracking module. So this figure is showing the tracking system which maintains the object identities across the frame in the highway scenarios. And also each detect vehicle is assigned with a unique ID, you can see. And we have 13 here, 17 here, and 22 here. And also then, also the class label, we have the car here, and also we have the truck here. So, and also the confidence source. So as the vehicle crosses this white line, and also it can be so the system can just update with the in and out counters. So this this capacity, this capability is critical for the applications such as the traffic analysis and also the flow estimation and also the smart surveillance. So this model both detecting the cars and the vehicles, and also the ID persistence also across the frame, which have number 1, number 2, also demonstrating the tracker's reliability, and also for the crossing logic. So it just like enable the traffic counting matrix, which, for example, if this one car just like go into this white line, we just counting in 1, in 2, in here. And also if this car just like go out of this line, we just counting like the alt 1, alt 2. And also for the real-time interface is feasible due to the lightweight trackers such as the Euro-V8 module, and also the efficient tracker like the BiTrack and the DeepSort.
I'm Joe. I'm going to walk through the structure of our code and explain how each part of this code works, from the data pre-processing to training the models and inference evaluations. Starting from CMFC, it is a framework for single object tracking. We use the object tracking benchmark 100 datasets. For each video sequence, we generate pairs of images, a template image Z and a search image X. Sample with a fixed frame gap. We use the OpenCV's getRecSubPix to crop both the template and the search region based on ground truth bounding box provided by the dataset. Then we resize them to 127 by 127 and 255 by 255 respectively, and normalize them into the PyTorch tensors. And our CMFC model is a fully convolutional Siamese network implemented from scratch. So it has 5 convolutional layers shared between Z and X, the template image and the search image, followed by a custom cross-correlation operations to produce a response map. These response map will highlight the similarity between the templates and the search region. We train our model, our CMFC model, for 5 epochs using the Atom optimizers, and we choose a relatively more conservative or standardized learning rates and wait decades. And in terms of how to use this model, first we should go to cell 3 in our convolutional network in our IPy notebook. By clicking on cell 3, we make sure that our CMFC model is well constructed, and then we went to cell 9 to load the video which is gonna be processed by our CMFC model. And once you click on the run, you will see this window get pop up, and we can manually select the object in this video that we want to track. And by hitting enter on your keyboard, you're gonna see the CMFC. It's tracking out the object that we selected, and in this process, we can observe that there's some kind of drifting occurring while tracing the targets, and then we started to evaluate our model, and starting by looking at this response map. So this response map actually I think it's very successfully highlighted the targets area, showing a good initial locations. And we plot the IOU over frames for the basketball data sets. And this plot, by reading them, we can see this is a very unstable tracking. The IOU drops after spraying 300, suggesting the trackers fell after occlusion or faster movement. The center distance, we also have a plot for the center distance arrow. And this pixel arrow increase over time, and which its peaks at around 100 frame, and which have a drift of 450 pixels. So after introducing the single object tracking, we can move on to multi-object tracking using the deep sort. On the dataset side, we use the multiple object tracking 20 datasets, and in this dataset, each video was split into individual frames. We ran YOLO V8 on this video to obtain the bounding boxes at the very first frame to get its starting locations. And after that, we initialized our deep sort tracking by using Kalman filter for motion prediction and appearance embedding using the mobile nets. And our tracking ID managers was a max age of 10. We also added EMA smoothing for each object size to improve visual consistency. Every YOLO V8 detection is passed to deep sort. For each frame, the motion prediction is performed using the Kalman filter. Matching is done using the Hungarian algorithm on both IOU and appearance vectors. And EMA is applied to the size and position simultaneously. Regarding the evaluations, we kind of do a quick comparison with the ground truth TXT from the multiple object tracking 20 datasets with the outcome annotation of our trackers. And we put this into the MOT challenges framework, which is called Track Evolve. And then we come out with a table of HOTA and MOTA. And by reading this table here, we can see the HOTA score, it's relatively slow on this deep sort combining with EMA. So this is meaning that it has a problem with the ID consistency. And there's even negative MOTA score indicating frequent false positive, so which means it has more false detection than correct detections. Regarding its plot, after you evaluated, compare those data from ground truth and your trackers, you came to this location of deep sort EMA, then you can find this plot have several legends, and we can see that the HOTA line and the determined A line are stay low across the alpha value, but the location A is high, showing good spatial precision, but it does have a very bad identity tracking. And since this sort of method has a very low consistency and continuity in tracking the ID, we try to fine tune our model. So we also tried another approach using the Kalman filter. So this time we didn't apply the EMA for smoothing with the motion and the frame size. So we kind of just use the baseline Kalman filter, and in this video demonstration we can see that the ID it's more consistent than the last one. It has longer continuity on this prediction spindle, and when we compare the tracker data with the ground truth from MOT20 datasets, we do got relatively higher score on HOTA, and we got a positive score on MOTA as well. So that means that basically just means it has better identity associations and stable trackings. We can just have a glance of the outcome of this deep sort Kalman filter versions. Compared to the last one, it has relatively more stable curve and show better tracking reliability and fewer dropped IDs. So after having some using experience of CMFC and deep sort, our group find that we're not satisfied with the performance continuity with deep sort and CMFC. So we decided to have a few tries with other models and frameworks. And among this framework, BITRAC stood out from all of this. And the way that we use BITRAC is kind of similar to deep sort. So same as before, we use YOLO V8 to detect the target in MOT20 videos. So, and after that, BITRAC is initialized with parameters of track stress, match stress, and track buffer. And it uses a dual association strategy. So first, it match high confidence detection, then it will match the lower confidence detection to the missed tracks. So when BITRAC is processing this, in every frame, BITRAC gets YOLO detections and run Hungarian matching twice, high and low confidence, and save tracks in the MOT format. And after comparing the ground truth from MOT20 datasets and the output of BITRAC trackers, we get this relatively better performance than deep sort. So by looking at this data here, BITRAC have the highest HOTA score, and also with a good determined A and associate A. It also have a very high MOTA score as well, and so there it means that there are fewer ID switches and more accurate tracking. So by looking at its plot here of BITRAC, so in this plot, the HOTA and the other curves degrade slowly as alpha increase, showing a strong robustness and ID preservations. The flat and high the location A indicate a strong spatial accuracy as well.